Good afternoon. This talk is Securing Kubernetes Clusters in the Cloud in Calgary 2020. My name is Amiran Alavidze. I'm Director of Security at Desktop. We are a Vancouver-based startup helping companies succeed in their digital transformation journeys. You can connect with me on Twitter. I'm at airman604. As security people, we're often thrown into something we have no idea about. This project goes live in a week, go figure out and make it secure kind of thing. To me personally, this is not a bug, this is a feature, this is a core characteristic of our roles as security professionals. And this is exactly what happened to me with Kubernetes. We were launching a new application, a cloud-based application, and Kubernetes was going to be at the core of its architecture. And this talk is essentially the amalgamation of many months of learning, threat modeling, and incrementally improving security of our production Kubernetes clusters. And by sharing this, I hope you'll be able to benefit from our experience. To begin with, let's talk a little bit about Kubernetes itself. Kubernetes is open source, a container orchestration platform that originated at Google. It was designed from the ground up as a loosely coupled collection of components centered around deployments, maintenance, and scaling of workloads, essentially applications/containers. It has very good support for declarative deployments and immutable components. Let's go through some of the terminology to begin with. It all starts, as this is container orchestration technology, it all starts with images and containers. So image is essentially a template based on which the containers are built, and containers are workloads, applications that you run in your production. But in Kubernetes, the smallest deployable unit of computing is not actually a container. It's something that they call a pod. In many cases, a pod is a single container, but it doesn't have to be. A pod can be multiple containers, and they can share resources across those containers. They essentially have the same namespace for file systems, so they can have access to the same files. They can see the same files. And they also have access to the same networking. So they can actually talk to each other through the localhost interface. After pods, there's also things that are used to inject information into those pods. And those are config maps and secrets depicted on the right here. That's essentially a way to tell the pod, hey, by the way, your database is here, and your username to connect to it is this, and your password to connect to it is this. Essentially, any sort of configuration type information, so like Nginx config or Apache config and things like that, and or credentials can be injected into the containers through config maps and secrets. Then we have the actual scalability part of it, and that comes in the form of deployments. So deployments is a concept, is an object in Kubernetes that allows you to deploy multiple instances of the same thing. So it manages consistent number of replicas for the pods that you need to run, and it also manages things like rolling updates. So if you need to deploy a new version of your containers, you can do it through deployments, and you can set parameters around how that's done, whether you want to kill all of your old containers at once and then deploy all the new ones at once, or gradually kill the old ones one by one and deploy the new ones one by one. Under the hood, deployments also use an object that they call replica sets. Replica set is purely the scaling part of the deployment, so it only makes sure that if you said you're going to have 3 pods using this image, you always have 3 pods using that image. And if one pod dies, replica set makes sure that there's another pod that's being started. On top of that, there's a concept called a service. And the service is essentially a way for the Kubernetes cluster to expose those workloads that you run either to the outside world, so basically your users connecting in and using your application, or even within the container. So you can define internal services within the cluster as well. So if you have, for example, a web tier and the database tier, you can use service to expose the database to the web tier, and it's essentially a glue, a networking glue, a networking and DNS glue that ties those two components together. The last thing I want to mention is namespaces. Namespaces essentially are a way to logically group all the workloads, all the resources within your cluster. And for example, by default, it's used to segregate the control plane workloads that are part of the cluster itself from all of your application workloads. But it can be used for more things, and some companies are also using namespaces to host multi-tenant Kubernetes environments and have multiple customers using the same clusters, but still being segregated based on those namespaces. Now, having said that and mentioning some of the terminology, I want to cover briefly essentially the architecture of Kubernetes. This picture you can find in Kubernetes documentation. There's essentially two parts to any Kubernetes cluster. There's one that they call Kubernetes control plane, and that's one or more master nodes that run system components that makes up the Kubernetes cluster. The right-hand side of that is what they call Kubernetes nodes, and that's essentially worker nodes that talk to the control plane, but ultimately their core responsibility is to run your workloads, run your applications. So on the control plane, there's multiple things that are happening there. At the core of the cluster is something called etcd. That's essentially a configuration database that stores current state and desired state, all the data for the whole cluster. Then there's the kube API server. This is how everything within the cluster interacts with the control plane. So if you need to deploy something, or if one of the worker nodes needs to check or report its health status, this is all done through the Kubernetes kube API server. Then there's processes within the control plane that actually do all the management pieces within the cluster. One part of that is what they call kube controller manager. That's things that manage those pods and manage those deployments. Optionally, there might be a cloud controller management. That component is responsible for interfacing with the cloud service provider. So if you're running your cluster in infrastructure as a service type environment in AWS or GCP or Azure or any other provider, and you need resources that are used by the cluster that infrastructure as a service provider is responsible for, things like load balancers, etc. That's the component that kind of talks using the IaaS APIs and interacts with the cloud-based infrastructure provider. And the last main part within that control plane is the kube scheduler. That's the glue, or that's the magic that essentially is responsible for assigning specific workloads to specific nodes based on some predefined algorithms and predefined parameters that you can set for the cluster. So it takes into account things like free memory and current utilization of the nodes and any sort of affinity rules that you can set for your workloads. And it uses all of that to define that this workload goes to this node and this workload goes to that node. So on the right-hand side, we've got Kubernetes nodes. As I said, those are usually VMs that actually run the workloads, run the applications. The core component that has to be installed on every node is called kubelet, and that's the piece that talks to the API server and manages all of the local resources based on the commands from the API server. The other core component there is the kube proxy, and that's the glue that supports that notion of the service. It's responsible for any sort of network-based interactions and exposing of the services within the cluster, either within the cluster itself or to the outside world as well. Now, having said that, I want to give you a kind of an idea of how Kubernetes works overall and how all of these different things work together to provide that kind of consistent experience. So this slide, or the series of slides, is what I call a life story of a deployment. So let's say we create a new deployment. And by the way, this can be done either through in kind of imperative way, saying launching kubectl, which is a command line tool to manage your Kubernetes cluster, and saying, hey, create me a deployment. Or it can be done, which is usually the case in a declarative way. You create essentially a YAML file that describes all of the workloads, all of your environment, and you tell through kubectl again, usually you say, okay, I want to apply this end state, this desired state to the cluster, and then cluster does all the magic and provisions those workloads, etc. So let's say we create a new deployment, we run kubectl. Either way, everything in the backend happens the same way, whether you use imperative way of creating deployments or a declarative way, it doesn't matter. What kubectl does, essentially all it does, it connects to that kube API server and it tells it, hey, by the way, I want a new deployment. What happens next is the API server talks to that etcd database and it updates the state, updates the data in that etcd database. And then once that's done, this call is complete and kubectl returns back, you get your command prompt back. So now within etcd, you've got this deployment object all of a sudden. Within that deployment, this is essentially describing the desired state. This is telling Kubernetes cluster, I want this deployment. As part of that deployment, there will be a number of parameters. There's usually a name. You can say, I want this many replicas. There's also a definition of the template of each of the pods. So things like image name to run, something like Nginx or Ubuntu or whatever else you're using. Or in most cases, this is going to be some custom image that you've created using standard image plus some of your code, etc. So now we have this deployment object in the etcd database, and now comes that controller manager that is part of the Kubernetes control plane. The controller manager sees the deployment object in the database, but there's no corresponding replica set in the database. So it says, oh, that's an inconsistency. Let me create a replica set for you. And that replica set inherits all of those parameters from the deployment. So things like number of replicas, things like what image to run in the pods that this replica set manages, et cetera, et cetera. And then the same controller manager looks at the data in the etcd again, and it says, okay, I've got deployment now, I've got the replica set now, but there's no pods yet. So it creates objects for the pods. And again, those pods will inherit parts of the configuration from that deployment. So things like how many container is going to be in each pod and what image is going to be used in each of the containers. And now comes that scheduler that defines where those pods are going to run. And it does its magic algorithm, and it runs through it, and it essentially assigns each of these pod objects to a specific node. So it's important to say that up until now, no workloads are actually running. This is all happening within the control plane, and it's all happening. It's all essentially manipulating the data within the etcd database. Nothing's running yet. And this is where that part of the magic comes into play. So now kubelet, which is that component that runs on each of the Kubernetes nodes, checks with the API server and says, hey, is there any new work for me? Basically tell me my desired state that's defined in the database, and I'm going to make sure that my actual state is the same as the desired state. And API server checks with etcd and tells kubelet, hey, yeah, there is new work. And then it's the kubelet component that actually provisions all those containers now that it knows about the new pod that has been assigned to that node. It will work with the Docker as the underlying containerization technology, which is what Kubernetes is using by default, though it's not the only option nowadays. And it will provision the containers as part of the pods, and it will provision any sort of networking configurations and everything else that's been defined in that deployment. And this is where the actual work starts. One more thing that I want to talk about before we dive into the actual security implications of all of this is, why am I talking about cloud-based deployments of Kubernetes specifically? This all sounds almost magical and easy to manage and easy to use. Well, the matter of fact is that although it does sound magical and it sounds like it's easy to use, it's actually very hard to manage. And there's a number of really difficult problems to solve from engineering perspective if you're going to run your own, roll your own Kubernetes cluster. Things like high availability and replication of the etcd and all the networking part. all of that are not trivial problems. And also because Kubernetes is sort of, you can think of it as sort of like a Lego. All of those different things that I talked about, those are actually different projects that have different repositories on GitHub, for example, that roll into this one coherent system when applied together. But there's multiple ways to provision a Kubernetes cluster, and there's multiple ways to link all of those components, and which means there's multiple ways of making mistakes, and there's multiple ways of screw things up, especially in the long run, as you need to scale that cluster to support hundreds and thousands and tens and hundreds of thousands of the workloads. So if there's only one thing you take away from this talk is I highly, highly, highly advise you not to roll your own Kubernetes cluster, and if it is by any means a possibility, to look at hosted Kubernetes options. And there's all of the major cloud service providers support managed Kubernetes, and that's definitely something that will make your life much easier in the long run. So now that all of that is out of the way, let's talk a little bit about the Kubernetes threat model. Basically, what are all the things that we need to be concerned about? And for that, I'll come back to the architecture, because to me, it kind of visually, it's useful to map the things that I'll talk about to this architecture. The three main pieces where there definitely are things that relate to security that we need to be concerned about are two with the control plane. It's access to the control plane itself, access to the Kube API server, and access to the etcd database, because etcd database is the source of truth for the Kubernetes cluster. If I have full access to the etcd database, I can do anything I want with the cluster, including getting all the information out of it, including secrets and config maps, and/or creating new workloads and deploying new workloads, because that's essentially how Kubernetes works off the etcd database. Kube API server, again, anything that happens within Kubernetes is done through the server. So if you can find credentials and connect to that Kube API server, potentially you can do a lot of damage. And the third part is the worker nodes themselves. You are running workloads on those worker nodes. So if one of those workloads is compromised, that's essentially a door into potentially this whole cluster. Let's talk a little bit about the threat model. There's kind of four main things that come to mind when you think about Kubernetes. So attacks on the control plane. As I said, if you can connect to the control plane, to the API server, if you can find credentials, that's one way of compromising potentially the whole cluster. Second scenario is if there's a workload that we're running, if there's an application that we're running in the cluster and somebody hacks into that application, somebody compromised that application, potentially that could be a doorway into the cluster as well. User accounts and credentials, this works together with the attacks on the control plane. So credentials that could be leaked either through source code or inconsistent access controls and things like that could potentially be used to attack clusters. And the last piece is compromised images. If you don't trust the images, the workloads that you're running within the cluster, that could potentially be a way into the cluster as well. Kubernetes project has done in 2018, they've hired 2 companies and they've done a full audit of their architecture and full audit of their source code. And if you're interested, I highly recommend checking it out. All the reports that were the result of that audit, they've published on their GitHub. And it's an interesting bedtime reading for sure. Those reports are pretty big, but they talk about some of the core decisions that the project has made, Kubernetes project has made, and what are the implications of those decisions for the security of Kubernetes clusters. Out of those 4 things, the main thing that we definitely need to care about is the compromised applications. That's always going to be an issue because the reason to run Kubernetes clusters are those workloads that are part of the cluster. And if one of those workloads are bound to be compromised at some point of time, and you have to be ready and you have to analyze what that means for the security of the whole cluster itself and for the security of other things that are running in the same cluster. And so this is what I'll focus on throughout the rest of the presentation. And when we think about a compromised application, there's essentially three main avenues that can happen, three main things that can happen after that. The first one is network access and lateral movement. If I can access that container that runs my application, now potentially I can investigate what else is on that network and what else is running in that cluster and try to move laterally throughout the cluster. Fortunately or unfortunately, those applications are bound to have some access within the cluster. They might have access to a database, or they might have access to some other services that they need to use to provide the end user functionality, or in any sort of microservices type architecture. And so that lateral movement throughout the cluster is definitely a big risk that needs to be thought through and addressed. The second piece is Kubernetes cluster credentials. In a lot of cases, there are Kubernetes credentials in those workloads, and we need to understand what those are and what we can do to secure them further, and how they can be used to gain additional access within the cluster based on the compromised application. And the third avenue is container escapes. This is essentially saying, okay, there's this node that runs a bunch of workloads. I've compromised this one workload, this one application. If I can now escape out of that container and gain full access to the node itself, I can potentially get much more information out of that and maybe even take over the whole cluster itself. So let's talk about those three things in a little bit more detail. And the first one is the networking. Networking is quite an interesting component of Kubernetes in a sense that it's not a core part of the Kubernetes project. Networking in Kubernetes clusters is provided through plugins, and they call the system CNI, Container Networking Interface. But essentially, networking plumbing essentially is not part of the cluster itself. It can be deployed, and there's multiple different networking plugins that are available and can be used, but it's an external dependency for that cluster in a sense. At the core of the Kubernetes is an open networking plugin. If you look at the documentation, the Kubernetes documentation, it essentially says that it's a fundamental underlying assumption that any node within the cluster can talk to any other node within the cluster without any sort of network address translation. This doesn't mean that any workload that runs within the cluster will have unlimited access with unlimited network access within the cluster, but that does say that it's an additional step that you need to make, and you need to make sure that that's happening, because by default it's all going to be open to everybody. And so that layer of network level security with the ability to segregate that network-based access is done through something that Kubernetes calls network policies. It's natively supported construct, meaning that you can define network policies for a cluster. But the important piece here is that those network policies have to be supported by the networking plugins, and not all of the plugins support network policies. So why is it important to limit network access to the workloads? There's several things that are happening there. Three main ones are instance metadata access. So we all remember the Capital One data breach and how it happened. This is essentially cloud service provider credentials and other sensitive information that is exposed through that metadata endpoint, the well-known 169.254.169.254. If a workload has access to that metadata endpoint, potentially you can be exposing the cloud service provider temporary credentials. You can be exposing credentials that are used within the Kubernetes cluster, because there's often credentials that are used throughout the node provisioning process that the node uses to join into the Kubernetes cluster. And in some cases, this escalation or this security issue doesn't require full compromise of the application and can actually be done through vulnerabilities such as SSRF. So you don't necessarily need full access to the container. You might use this even without that. The second piece is the control plane access. By default, everything that runs in your cluster has access to the Kubernetes API endpoint. So think about this. Any workload that you have in the cluster can talk to the control plane of your cluster. It's exposed by default. There's encryption, again, by default, usually enabled there. But essentially, that access is something that potentially needs to be protected. And the third piece that we talked about is the lateral movement. So it's things like access to databases, access to other services or microservices within the cluster. And sometimes those microservices are assumed to be running in a secure kind of segment, secure environment, and don't always require authentication. But if you've got a workload that's exposed to the internet and it doesn't need access to this sensitive database, then at a network level, you can improve your defense in depth, but by blocking that access through the network policies. One more thing that I want to mention here is this thing called Helm. Helm is essentially a package manager for Kubernetes. So it allows you to combine different containers, pods, and components and services into this one description that can be deployed as a single application that can be consisting of multiple components working together. It's very often used in Kubernetes clusters because it's fairly popular and it's an easy way to deploy some of the kind of dependent services that are not part of your code base that your application might be using to work. The interesting thing here is that there's basically two major versions of Helm, version 2 and version 3. And it's very important because they work very differently. So Helm version 3 uses this component that's depicted on this picture called tiller. And it's the tiller actually that's doing everything, doing all the deployments that you run through Helm, which means that it's the tiller that actually holds privileged access within the cluster. It can read secrets, it can deploy new workloads, it can check the status of the cluster and potentially do other things as well. Which also means that if somebody has network level access to the tiller, they can escalate, that might be an avenue for them to escalate their access within the cluster to the privileges of the tiller, which is fairly broad privileges usually. Another important thing about version 2 is, and this is a quote from their documentation, they plainly say, default installation applies no security configurations to the Helm deployment itself, which means that tiller does not even do any sort of authentication. So unless you've put those network policies in place, just having Helm version 2 deployed in your cluster could be a potential security concern. All right, the third piece we talked about is cluster credentials. Kubernetes supports a number of options for authentication that use certificates internally. They can do token-based authentication. They can do basic authentication with just username and password. And they also support integration with external identity providers through OpenID Connect. Interesting thing is that Kubernetes itself, the core project, does not have a notion of a user. It essentially assumes that users are managed outside of the cluster, and Kubernetes does not want to be concerned about those users. What this means is users are managed through those external integrations through OpenID Connect, and you don't manage users within the cluster itself. It's an external, a completely external thing that you need to be configuring. But what Kubernetes does manage is those service accounts, and service accounts are used within the cluster to provide access for things that run with the cluster, within the cluster, that they need access to the Kubernetes API. By default, every pod is assigned a service account. Even if you don't do it manually, it will be assigned a default service account that's tied to the namespace in which that pod is running. But any workload by default in Kubernetes is assigned a service account. And again, by default, credentials for that service account are mounted in the pod, which means that if you don't do anything, you've got a workload running, that workload is compromised. Now somebody who compromised that workload has access to those credentials. And while they're limited and mostly read-only, it's still some access to the cluster that can potentially be escalated further. In terms of permissions and managing access, Kubernetes does what they call Rbac, role-based access control, and that is managed through kind of two sets of objects. One is role and role binding. So role is essentially a definition of access parameters within the cluster, and role binding links that role to a specific either user ID or a service account. And there's also a very similar cluster role and cluster role binding. The only difference between the two is that role is limited to a specific namespace, and cluster role and cluster role binding are applied to the whole cluster. And the third avenue for the threat model that we talked about was container escapes. Container escapes potentially can be done in multiple ways. There could be vulnerabilities in the container runtime as well, something like runc or the Docker. It could be done through outdated kernel, through essentially a kernel level privilege escalation vulnerabilities. It could be done through security misconfigurations. So things like mapping Docker socket into containers so that container can now interface with the Docker and like launch containers and ask for things. Or mounting of sensitive paths, especially things like /etc that hosts like password hashes and things like that within the container. There's also this notion of privileged containers. Sometimes things that you run in your cluster need privileged access to the host itself. In a lot of cases, that would be things like log management solutions that collect logs from the host and from other containers. In some cases, it will be security tooling that need to interface with the host at the low level and have privileged access to what's happening on the host. But ultimately, if you have workloads running as privileged containers, that is a really bad idea, because that essentially means if that workload is compromised, by default and by definition, anybody that compromises that workload has full access to the host itself. And the last important question here is the question of user IDs for the containers. It's considered best practice to run processes within containers and as non-root user ID. In practice, though, majority of at least the public images that you'll come across, probably more than 80% of them will have by default the container processes running as root. And that essentially limits your avenues or limits that containment and allows for easier container escapes. It usually needs to be coupled with other things on this list. In itself, it's not necessarily sufficient to be able to escape out of the container, but it's more like a defense in depth type of control. So now that we're sufficiently scared about Kubernetes and the security of the clusters, what do we do? Important thing here is that back to that idea of not rolling your own Kubernetes clusters, a lot of the things to secure the Kubernetes and specifically the control plane of Kubernetes will be done by your cloud service provider if you opted for a managed Kubernetes service. So let's talk about specific things you can do to secure your clusters. First, and probably the most important part, is the network policies. This is my firm belief. As we said, network policies are native Kubernetes way to restrict network access within the cluster. Again, as I said, it's not core functionality of Kubernetes itself. That's provided by the networking plugins, and not all of the plugins support network policies. Moreover, by default, if you provision a Kubernetes cluster in either Azure or AWS or even Google, the default network plugin that they use does not support network policies. What this means is even if you apply network policies, firstly, they won't work, they won't be applied. Secondly, you won't even get a warning. Like if your networking plugin doesn't support network policies, but you apply network policies, there's not going to be any warning until you test or until you verify that, until you switch that networking plugin to the one that does support network policies. By default, all the traffic within the cluster is allowed. This is true even for network plugins that do support network policies. This is the default state. It's all open by default. This is even more important because even if you do apply policies, again, by default, there's no network level segregation between those namespaces. As I said, they're more, from the get-go, they're more of a logical way of grouping the workloads. And if you are relying on the namespaces as a way to segment your workloads, maybe you want to run your more sensitive workloads in a more isolated environment, you need to make additional steps to make sure that that namespace is actually segregated appropriately. Network policies support both inbound and outbound rules. So this is essentially like security groups in AWS. This is a way to natively support network filtering and network access controls within the cluster. This is what a typical network policy might look like. You basically give it a name, you give it the rules. In this case, this specific one opens port 6379 from a front end or from a workload from a container labeled as front end to a container labeled as database. Credentials. We talked about access to that instance metadata endpoint. That access definitely needs to be protected. You can essentially take two routes to be able to deal with that. You can either apply network policies and just restrict access to that magic IP address where the instance metadata is running, or you can use, now all of the major cloud service providers, they support assigning IAM permissions, essentially permissions within the cloud, your cloud infrastructure, to specific workloads. So they can be more granular than just the whole host. They can assign those permissions to the individual workloads. What that means is, even on a single node, if this workload, this container makes a call to the metadata endpoint, it will get different credentials than if this container makes a call to that same endpoint. AWS calls this IAM roles for service accounts. Google calls this GKE workload identity, and Azure calls it Azure Active Directory pod identity. And this is the preferred actually way to secure that instance metadata access. The second part that relates to credentials is Kubernetes credentials. As I mentioned, that service account is mapped by default into every workload that runs as part of the cluster. That is controlled through a setting of the pod called auto-mount service account token. I highly recommend disabling it. The reason being, in majority of the cases, probably 99% of all the cases, your applications, your workloads do not need direct access to the Kubernetes cluster. They do not need to talk directly to your cluster. And so in majority of the cases, it's just the best to, again, this might be a defense in depth because by default, it doesn't give much access to the cluster, but it is that additional layer that you can put in place to secure credentials of your clusters. And then you would usually use your cloud service provider to manage access to the cloud cluster itself. So you'll have IAM users that will be assigned credentials through the Azure, Amazon, or GCP, and they'll use the same accounts that they use to access the cloud infrastructure to log in and to manage the Kubernetes cluster. Now, access to the control plane, there's two things. One thing we already talked about, which is access to the control plane from workloads within the cluster. It's enabled by default. Again, as with service account, in majority of the cases, that access is not required to your workload, so it's a good idea to limit it based on using the network policy. There's another side of things here. By default, when you provision a Kubernetes cluster in all three major cloud providers, that cluster will get a public endpoint, public API endpoint, meaning that you can, if you have credentials, you can interact with cluster and you can manage the cluster through the internet, hitting directly that public API endpoint. Again, good idea from defense and depth perspective to only limit that access to either from your cloud environment or maybe from the IP addresses assigned to your corporate network, and so that that endpoint is not just publicly exposed. And then the last plane that relates to control plane, the last piece that relates to control plane is keeping Kubernetes itself up to date. This is where partially your cloud provider will help, meaning that they, to some extent, have that process automated. You still, in most cases, need to initiate the update, though. So in Azure and in AWS, that initiation is a manual step that you need to make. You can basically, you have to tell the cloud service provider, I want to upgrade this node, then this node, then this node, and then the control plane. In GKE, that can be fully automated. You basically can tell GKE to and say, I want to keep my cluster always up to date, keep it on this version branch of Kubernetes, and it will do all the magic in the background. Securing the workloads themselves. So this is along the lines of protecting from container escapes. This is done through a parameter called security context that can be defined for each of the pods. They allow you to specify that the payloads, the workloads in that container should run as non-root. You can disallow privileged pods. So remember that privileged flag that I talked about that gives full access to the host. You can disable privileged escalation, which essentially will make the setuid binaries not work. And you can disable things like host file system mounting. So security context is a way to set those parameters on individual workloads, individual pods or deployments, but you can also enforce those parameters globally across all of the workloads in the cluster using something that's called pod security policy, or a newer mechanism that Kubernetes is gradually migrating to is something called OPA, or Open Policy Agent. What that piece allows you to do is to say, nothing in my cluster can run as root user. And essentially, if somebody tries to deploy something and they forgot to set that security context and forgot to run the workload as non-root user, pod security policy will prevent that workload from being applied. And last piece with securing the workloads is keeping the operating system and the kernel up to date. So that essentially allows you to protect from kernel privilege escalation vulnerabilities. In Azure and AWS, that's a manual upgrade process. You need to initiate it. In GKE, even this step can be automated. So in terms of keeping your operating system and nodes and Kubernetes control plane itself up to date, in GKE, you can basically automate it end-to-end if that's what you want to do. Some more things with regard to securing the workloads. There's options potentially for better container isolation. Only Google at the moment supports one of these. They're rolling out something that they call GKE Sandbox, which uses a technology called gvisor, and that essentially allows better segregation through the fact that the kernel that the containers see is not the actual kernel of the host. It's a userland emulated kernel. So it basically adds that another layer between the container and the host, so that even if there is a privilege escalation vulnerability in the kernel, chances are containers won't be able to use that because that's not the kernel that they interact with. The other option here is something called Kata. I don't think any of the cloud service providers support this yet, but the idea basically is that instead of running workloads as truly containers, they essentially instantiate a micro VM for each of the containers and provide a much better isolation for the workloads. Securing your images is definitely another big thing here. So things like making sure that you're using trusted images to run in the container, or use trusted images as the base image for your own containers and images, scanning for known CVEs and missing patches, and also migrating to minimal images. So basically making sure that things like compilers and shells and things like that, things are not usually needed within the containers, are not available, are not even present in the container. So if the workload is compromised, this is another one of those defense in depth type of controls, in a sense that they make it harder for somebody to do anything with that container, even if the workload is compromised. couple last things worth mentioning. If using Helm, upgrade to version 3. Version 3 does not have the tiller that is a big headache from security standpoint. They basically use the same credentials that developers or engineers would use when they use kubectl to connect to the cluster and to provision those workloads. That's done through Helm. Logging is a big thing. So there's some logging available in Kubernetes, the Kubernetes control plane with deployments and workloads, etc., and some application level logging, and make sure that essentially anything that runs within the cluster is usually ephemeral, which means that it can die at any point of time. So if you need the logs, you need to extract the logs on an ongoing basis from anything within the cluster that you care about. I want to spend the last 5 minutes of the talk to talk a little bit about what I call cloud-native security solutions. I'm not going to mention any of the vendor names. Feel free to ask me after the talk through Twitter or through Hop. But what those cloud-native security solutions allow you to do is multiple things. First part is they can check the configuration of your cluster, and usually they do it using the CIS benchmark, Center for Internet Security, and basically in an automated way tell you the things that might be worthwhile addressing. They also do image and container vulnerability scanning, so finding known CVEs within the components that are present in images and containers. Images is essentially done on a registry that you run. If you have your own private image registry, they can scan the whole registry and tell you issues with the images in that registry. And container side is they essentially look at everything that's actually running at this moment in your cluster and do the same kind of vulnerability scans for those containers. The third piece that they do, and this is the most interesting to me personally at least, is behavior analysis of what's happening within the containers. You can think about this as EDR for cloud-native clusters, for Kubernetes clusters. They look at processes that are running in those containers, and they look at things like syscalls and file operations. And there's two kind of approaches of what they do with that information. There's either a rule-based approach, so things like, oh, if bash is started as a child process from Tomcat or Apache, that's probably not a usual situation, and I'm going to alert you based on that. So basically rule-based, those rules have to be predefined, and they're usually provided by the vendor themselves. Or there's also anomaly-based approach, which basically says that, oh, I'm going to watch this container for a while, let's say 24 hours, and note all the things that it's doing, what processes it starts, what syscalls it makes, what files it opens or changes, or even down to the network connection level. And then everything outside of that profile that I've built, that I've learned, if anything happens outside of that profile, I'll alert you or block it going forward. And most of the solutions can either be deployed in blocking or alerting mode. With blocking, you basically can disallow those actions that don't meet the policy that you've defined. Some of the solutions also give you that cluster level network traffic control. This is basically very similar to network policies. My personal view is that you should rather use network policies because it's the native Kubernetes way of applying this mechanism. And they also have usually forensics capabilities, meaning that they allow you to extract forensics data out of compromised containers. Keep in mind, all of this is ephemeral, and like containers die and get restarted, and stuff happens to them all the time. And if you want to preserve any of the information, such as logs or memory dumps and things like that for incident response purposes, there's no native tools that are available for that. So this is the gap that the cloud-native security solutions address. Couple last slides. There's a bunch of open source tools that help you secure clusters. There's KubeBench, KubeHunter. Those do checks on your cluster. First one does the CIS benchmark checks, and the second one does a more broader cluster configuration checks. There's things that can scan for CVEs in images. That's Trivi, and Falco is that rule-based behavior monitoring tool. All of these are open source, and you can use them anytime for free in your clusters. Some resources, if you want to learn more, I highly recommend the first one that's listed. It's called Introduction to Kubernetes. It's a free official CNCF training about Kubernetes. and it's actually pretty good. And they host it on EDX, so go check it out. It's not too long. And it covers quite a lot of things. With that, that's all what I had for today. As I said, again, you can connect with me on Twitter. I'm at airman604. I'm also co-organizer of a local Vancouver-based DEF CON 604 group. If you are interested, we have monthly workshops and technical talks. If you're interested, you can check us out on Meetup. And with that, thanks very much.